Welcome to another lesson in vector calculus. Today, what I'm going to talk about is Jacobians. So in order to do that, we're going to start by looking at something you have always taken for granted. It's not that hard, but we're going to look at it a lot more deeply, and we're going to look at geometrically what U substitution is all about. And then we're going to expand on U substitution and say, what if we do that in two-dimensional space? So we'll talk about the change of coordinates in R2, which will be a little like U substitution, but more advanced, more sophisticated, and of course more work. And then we'll move to R3 and see what if we change coordinates in three-dimensional space. And we'll find out for both of these how we can relate this with integration. So let's look at a little U substitution problem. We have the integral from 0 to 3 of x times the square root of 1 plus x squared dx. So hopefully you know that the first step would be to let u equal 1 plus x squared, and the next would be to say that du is 2x dx. But my guess when you do this, you don't even think about really what's going on, why this works, and what's happening. So let me draw a picture. What we have here, because the integral is going from 0 to 3, and u is 1 plus x squared, 1 plus 0 squared is 1, 1 plus 3 squared is 10, so we could say that the line segment from 0 to 3 gets mapped to the line segment from 1 to 10. But there's more to it than just that. The question is, how is it mapped? It turns out it is not uniformly stretched out. That's what the du is all about. So for example, if we took a little delta x line segment next to the number 2, and we want to find out where to place it and how much to stretch it. So first thing, 1 plus 2 squared is 1 plus 4, or 5. So we know the center of the interval should be at 5. But the width gets stretched out, and du tells us how that stretching happens. So 2 times x is 2 times 2, which is 4. So that tells us the new width will be 4 delta x, 4 times the original width. So what we want to do is take this idea of U substitution, which changes the line interval to another line interval, but also talks about how you're stretching in different locations. And we want to bring that to a discussion in R2. So now let's suppose we have a transformation of the plane. This transformation is defined by u equal x minus 2y and v equals 2x minus 2y. We can start out with, instead of a little interval, we can start out with a square. The unit square, 0 to 1, 0 to 1. And see, where does that square go when we apply the transformation? Notice if you plug in 0, 0, that's this corner point, you get u is 0 and v is 0. So far so good. The origin goes to the origin. If you plug in 1, 0 on the other hand, you get 1, 2. And that's his point way up here. If we plug in 1, 1, then we get 1 minus 2 is negative 1, and 2 minus 2 is 0. So we get negative 1, 0. And there's this point. And then finally, if you plug in 0, 1, you get negative 2, negative 2. And that's this fourth point. If we connect the dots and shade in, we don't get a rectangle, we get a parallelogram. Notice when we use this transformation, interesting things happen. Start out with a square, you end up with a parallelogram. What we want to do is we want to find out what's going on, what's happening at every point, and how is the area adjusted. In one-dimensional space, you let u equal something and then you took a derivative. In two-dimensional space, That's not going to work. There isn't a derivative of the function of u and the function of v. There's 4 different derivatives. So we're going to define the Jacobian, and that's going to combine all 4 derivatives. Here's the definition. Let x equal the function g of u comma v, and y equal the function h of u comma v. Be differentiable. Then the Jacobian is del xy over del uv, and that's equal to the determinant of the matrix of partial derivatives. Del x del u, del x del v, del y del u, and del y del v. If you take that determinant, you get del x del u times del y del v minus del x del v times del y del u. And that's the Jacobian. That is going to play the role of du when we're talking about change of coordinates in R2 instead of R1. So here's an example, and it's the one example we have seen already. And the question is, find the Jacobian for polar coordinates. So polar coordinates, if you remember, are x of r theta is r cosine theta, and y of r theta is equal to r sine theta. We take the derivatives. Partial derivative with respect to r of x is just cosine theta. The partial derivative of x with respect to theta, derivative of the cosine theta is negative the sine theta. The r is a constant, it stays there. So you get negative r times the sine of theta. The partial derivative of y with respect to r is just the sine of theta. And the partial derivative of y with respect to theta, the derivative of the sine of theta, is just the cosine of theta. So we get r times the cosine theta. We put that into a matrix, and we get the determinant of the cosine of theta, negative r times the sine of theta, r cosine theta. And we multiply that out. We get cosine theta times r cosine theta, which is r cosine squared theta, minus a minus, r sine theta times sine theta, so that's plus r sine squared theta. But take a look at what we have. We have r cosine squared theta plus r sine squared theta. That's the same as r times cosine squared theta plus sine squared theta, and that's just r. But that shouldn't be too big a surprise that when you're doing a change of coordinates to polar coordinates, we're going to have an extra r. So here's the big theorem for two-dimensional space, and that's called the change of coordinates theorem. And it says, let the one-to-one transformation t go from R2 to R2 be given by x equal x of uv, y equals y of uv. Have non-zero Jacobian and continuous partial derivatives from a region S to a region R. Then the double integral over the region R of f of xy dy dx is equal to the double integral over the region S of f of x of uv, y of uv, times the Jacobian del xy over del uv in absolute values, dv du. So that's a big theorem. That tells us how to change coordinates and still get the integral that's correct. So here's why it works, just an idea. Let's suppose we start with a rectangle. And the rectangle has a left bottom point, u comma v, and sides delta u and delta v. Then if we take the transformation, uv gets transformed to xy, and we're not going to quite get a parallelogram, but it won't be that far off. And if it's continuous, it'll be very close. So the question is, what are the adjacent sides to this parallelogram? So let's see where the transformation sends u plus delta of u comma v. That's this point right here. And by general theory, that's equal to t of uv plus the partial derivative of x with respect to u times delta u, comma, the partial derivative of y with respect to u times delta u. So it says start at your point and add your little increment by taking the derivative. That's like f prime times delta x, except we have two variables now and two different functions. Similarly, if we want to find out where this point, this upper left point goes, then we say that t of u comma v plus delta v is about equal to t of uv plus the partial derivative of x with respect to v times delta v, comma, the partial derivative of y with respect to v times delta v. So if we want to find out the area of this parallelogram, the area of a parallelogram is the magnitude of the cross product of the two adjacent sides. So we take I, j, k. Notice that this first adjacent side at the bottom it looks like it's in two dimensions, so we can always say that the k component is 0. So we have xu, delta u, yu, delta u, and 0. Similarly, the next adjacent side has components xv delta v, yv delta v, and 0. Now we take the cross product. Notice the I component is 0. The j component is also 0. But the k component is xu delta u, yu delta v, minus yu delta u, xv delta v. So both of these terms have a delta u delta v. I can pull those out. And I get the quantity xu times yv minus xv times yu, delta u delta v. But this quantity in parentheses is the Jacobian, del xy over del uv. And that's the basic proof of this theorem. So let's take a look at an example. The question is, find the double integral over the region of x squared plus 4y squared dy dx, where r is the first quadrant of the ellipse x squared over 4 plus y squared equal 1. So let's start out by thinking about what coordinates we might want to use. If we let x equal 2r cosine theta and y equals r sine theta, that looks like elliptical coordinates for parametric equations. And it will work because notice that x squared is 4r squared cosine squared theta. If you divide by 4, you just get r squared cosine squared theta. And if you add r squared sine squared theta, you just get r squared. So if r goes from 0 to 1, that gives us that ellipse. Theta will go from 0 to pi over 2 because it's the first quadrant. Let's find the Jacobian. Del xy over del r theta. The partial derivative of x with respect to r is just 2 cosine theta. The partial derivative of x with respect to theta is negative 2r sine theta. The partial derivative of y with respect to r is sine theta. And the partial derivative of y with respect to theta is r cosine theta. I take a determinant, and I get 2r cosine theta, which is 2r cosine squared theta. Then we have a minus, that's a plus. 2r sine theta times sine theta, so that's 2r sine squared theta. And 2r cosine squared theta plus 2r sine squared theta, just 2r. Notice I don't need the absolute values because r is not negative. R goes between 0 and 1. We talked about that already. And theta goes between 0 and pi over 2. Now we integrate. The integral from 0 to pi over 2 of the integral from 0 to 1. So now let's talk about this x squared plus 4y squared. This is nice because if I take x squared over 4 plus y squared and multiply by 4, it looks like I get 4, except, remember that was 4r squared. So that gives us that x squared plus 4y squared is 4r squared. The rest is just 2r, because that's a Jacobian, dr d theta. And now I can integrate this. The integral of r squared times r, that's r cubed, r to the fourth over 4 times 2 is r to the fourth over 2, which is just 1/2, times 4 times pi over 2 is pi. This would have been very difficult to do without a change of coordinates. So this really demonstrates how important Jacobians are. So I want to mention a theorem that's very useful, and we're going to use it a little later on, and it's Jacobians and inverses. The idea is that sometimes, instead of having x as a function of uv and y as a function of uv, sometimes you have u as a function of x and y, and v as a function of x and y. Just like sometimes when you're doing u substitution, you let u equal some function of x and find du, but then there's the other kind of u substitution. That is done when you're dealing with inverse trig substitution. So sometimes you go forward, sometimes you go backwards, and we want to be able to handle both ways. So if there's a non-zero Jacobian and the partial derivatives are continuous from s to r, then the Jacobian del xy over del uv is equal to 1 over del uv over del xy. This seems obvious because I just divided fractions by taking the reciprocal and multiplying, except that the Jacobian is not a fraction, even if it looks like it. It's a determinant of a matrix of partial derivatives. That's just notation to make it easy to remember. I'm not going to prove it, but the idea is if you understand matrices, then the determinant of the inverse of a matrix is equal to 1 over the determinant of the matrix itself. Let's look at another example. Let's suppose we have the double integral over a region R of x plus 2y quantity squared times 4x plus 2y dy dx, where R is in the first quadrant and bounded by x squared minus y squared equals 1, x squared minus y squared equals 9, x plus 2y equals 3, and x plus 2y equals 6. I could draw this. It's not that bad. We get pieces of 2 hyperbola, and we have 2 lines, and we get a region. The next step usually is to put the little man in, little integral man. Here's the problem. You always want little integral man to be smiling and happy. If I put little integral man in here, there'll be nothing to smile about. You just see one big fat frown, and that's because the head goes from one curve to another, the feet go from one curve to another. You'd have to separate it into 3 different integrals, take inverse, it'd be horrible. Instead, what we can do is we can do a little change of coordinates. And here they are. Notice we have x squared minus y squared is between 1 and 9. We have x plus 2y is between 3 and 6. So we let u equal x squared minus y squared and v equal x plus 2y. And then the Jacobian is very easy. The partial derivative of u with respect to x is just 2x. The partial derivative of u with respect to y is negative 2y. The partial derivative of v with respect to x is 1. And the partial derivative of v with respect to y is 2. So I take the determinant of the matrix 2x, negative 2y, 1, 2, and I get 2x times 2, that's 4, minus a minus, 2y times 1. So I get 4 plus 2y. Nice and simple. And now what I can do is I can look at the transformed coordinates and see what we get. But before I do that, we should check one more thing. 4x plus 2y, you have to check to make sure it's positive. Because remember, we're taking an absolute value, but we're staying in the first quadrant. And because we're staying in the first quadrant, 4x plus 2y is clearly a positive number. So that means I don't need the absolute values. That saves me a lot. So I can make little integral man, and notice how happy little integral man is. Look at that smiling face. And that's because the very happiest little integral man can ever be is walking in this beautiful rectangle. So the little feet are just at v equal 3, and the head is bounded by v equals 6. Notice the farthest left is 1, and the farthest right is 9. So now we can integrate. We're going to take an integral from 1 to 9, left to right, integral from 3 to 6, bottom to top. Be careful. Every time you get only numbers here, always check to make sure that it is a rectangle. If it's not a rectangle, you don't just get numbers. And then we had x plus 2y quantity squared. But let x plus 2y was equal to v. So that's just v squared. And now notice the Jacobian, del u del v over del x del y, is 4x plus 2y. But we need del xy over del uv. But our theorem said that del xy over del uv is the reciprocal of del uv over del xy. So the Jacobian is 1 over 4x plus 2y. And the good news is I have a 4x plus 2y. And 4x plus 2y times 1 over 4x plus 2y is just 1. So then it all simplifies. And then dv du. It's a very simple integral. You could do this in your head. You could write it out. You could use a computer. I don't really care. It's a very basic one. I got 552. So now let's move up a dimension to triple integrals. The good news is it carries forward very nicely. We can say the Jacobian for a transformation, when we have a 3-variable transformation, is the determinant of the matrix of all the partial derivatives, xu, xv, xw, yu, yv, yw, zu, zv, dw. And that the triple integral over a solid of f of x, y, z, dz, dy, dx is equal to the triple integral of the transformed solid of f of x of uvw, y of uvw, z of uvw. I know it's a lot of writing, but it's really just a basic expansion from the two-dimensional idea. Times the Jacobian, del xyz over del uvw, dw, dv, du. And that's the big theorem for triple integrals. So let's look at spherical coordinates. And we've looked at that before, but now we can really do it rigorously. If you remember, x was equal to rho cosine theta, sine phi. Y was equal to rho sine theta, sine phi. And z was rho cosine phi. Let's take the Jacobian of this transformation. We take the partial derivative of x with respect to rho, and I get cosine theta, sine phi. The partial derivative of x with respect to theta, the derivative of the cosine theta, is negative the sine of theta, and I still have rho sine phi. And the partial derivative of x with respect to phi is rho cosine theta, and then cosine phi. The partial derivative of y with respect to rho is just sine theta, sine phi. The partial derivative of y with respect to theta is rho times the cosine theta times the sine of phi. And the partial derivative of y with respect to phi is rho sine of theta cosine of phi. And then finally, the partial derivative of z with respect to rho is just cosine of phi. The partial derivative of z with respect to theta, there are no thetas in the z function, so you just get 0. And the partial derivative of z with respect to phi is negative rho sine of phi. So now I take the determinant of this matrix. It's a bit of a mess, but bear with me. We'll make it work. We take the cosine theta sine of phi, that's right here, times the determinant of this guy, which is just rho squared, times the cosine of theta, times the sine phi, or sine squared phi, and then minus 0. And then for the next coordinate, we have a negative, and then another negative because it's the middle column. And then it turns out that when we take the rest, we'll get a negative from this guy, and then we'll also get a negative because we're pulling it from the other side. So I have 3 negatives, and that becomes a negative sign. Then I have my rho sine theta sine phi, and we have a rho sine theta sine squared phi, and then minus, then we have our rho sine theta cosine squared phi. And then finally, for the last column, we take a rho cosine theta cosine phi, it's right here. Then we have a 0 minus rho cosine theta, and then cosine phi times sine phi. And there's a determinant. We can do a lot of simplification. So all kinds of places. So the first thing is rho sine theta sine squared phi plus rho sine theta cosine squared phi. That's the same as just rho sine theta. Second, we can look at this and realize there's a rho squared here, there's a rho times a rho here, and there's a rho times a rho here. So there's a rho squared in each of these 3 terms. So I can pull out the rho squared. I have a negative here, a minus here, and then I have a negative here, so I can pull out the negative and then make everything positive. I have a sine phi here, I have a sine phi here, and I have a sine phi here, so I can pull out a sine phi. And let's see what's left. So if I pull out a negative rho squared sine phi, then what I'm left with is this goes away. I just have the cosine of theta here times the cosine theta, so I get cosine squared theta times a sine squared phi. And then over here, we'd already noticed that we have the rho squared sine phi, and I'm left with sine of phi times the sine of theta. And what I have here is I have a cosine theta times cosine theta, which is cosine squared theta, times cosine squared phi. So what I get is a cosine squared theta sine squared phi plus cosine squared theta cosine squared phi, the first and third. That gives you a cosine squared theta right here. And then I had a sine squared theta here. So now I have a sine squared theta plus cosine squared theta. That goes away. I've also taken the absolute value. I can get rid of the negative sign, and I can say this is equal to the absolute value of rho squared sine of phi. And that's what we had before from spherical coordinates. It's a lot of work. So if you didn't follow it completely, slow me down, write it on a piece of paper, do it yourself, and hopefully you'll do the extensive trigonometry that I just did, and also arrive at the absolute value of rho squared sine of phi. So now let's use it. So here's the question. Evaluate the triple integral over the solid Q of z dz dy dx, where Q is the solid inside the ellipsoid, x squared over 9 plus y squared over 16 plus z squared over 4 equals 1, and above the xy plane. the first step is to come up with a good set of coordinates or a good transformation. And if I let u equal x over 3, v equal y over 4, and w equals z over 2, then notice that u squared is x squared over 9, v squared is y squared over 16, and w squared is z squared over 4. So if I add u squared plus v squared plus w squared, I have to get 1. And that tells me that the transformed solid is the unit sphere. I find the Jacobian of this transformation. The partial derivative of u with respect to x is 1/3. Partial derivatives of u with respect to y and z are both 0. The partial derivative of v with respect to x and z are 0. And the partial derivative of v with respect to y is 1/4. The partial derivative of w with respect to x and y are both 0. And the partial derivative of w with respect to z is 1/2. That's an easy determinant. Whenever you have a diagonal matrix, you can just multiply. 1/3 times 1/4 times 1/2 is 1/24. So now let's put it all together. We have a triple integral. I'm going to hold off on what the surface is for now. It is a unit sphere, but we don't need to go there yet. You'll see why. We have that z is equal to 2w. So I put a 2w for the regular integrand. The Jacobian was 1 over 24, but that was del u vw over del xyz. We had the theorem that said if you need to flip them, we also flip the fraction. And the reciprocal of 1 over 24 is 24. We get dw dv du. Over the solid, u squared plus v squared plus w squared equals 1. But that's a unit sphere, which means, of course, I should use spherical coordinates, which I do. So I get 2 times 24 is 48. W in spherical coordinates, that's the third coordinate now. And that's a rho times the cosine of phi. Then we had rho squared sine phi, because that's the spherical coordinate Jacobian. D rho d theta d phi, we have our radius, rho, goes from 0 to 1, because we said it was our unit sphere. We have our theta going from 0 to 2 pi. We mentioned at the beginning that this was above the xy plane, so that means phi goes from 0 to pi over 2. And this is not a hard integral. I'll let you work this out. If you're allowed to use a calculator or a computer, go ahead. Not too bad by hand. And I got 12 pi when I worked this out. So that's all I have to say today about change of variables and Jacobians. This is a deep topic with some tough concepts. It may look easy to watch me do it, but wait till you see trying to do it yourself, coming up with the right transformation. That's usually the hard part. So if you have any questions, please let me know. I'm always happy to help you out. If you have another instructor, please ask your instructor to help you out. Whether it's day or night or morning, have a great time, and I will see you at the next lesson. Thank you for watching this video.